morning, student. In this part, we are going to consider the potential energy of a sound wave. Potential energy of a sound wave. As you have already known, when a sound wave travels through a air column, the air column will get displaced from its original position. Okay, so in order to displace the air column from its original position, it has to do work on the system, and that work will be stored as the total energy of the sound or total energy of the air column. Okay, so you see, suppose this is an air column. Say its thickness was delta x and its area was A, and this is all the molecules of the air. Okay, then when the sound wave propagate through it, the air column will get displaced from its original position. That work done will be stored as a total energy of this air column, which we have considered. Okay, total energy will be the sum of kinetic energy plus potential energy. We have already calculated the kinetic energy part from this for this element. Then once we know the total energy, then we can easily calculate the value of the potential energy. So this is this way we are going to proceed. Okay. So, since sound is a gaseous medium, so whatever the work done on the system, it will be the PdV kind of work done. Okay, so work done dW will be equal to P into dV. Okay, here dV means what is the total change in the volume of this air column as the sound passes through the medium, and capital P in this case will be the pressure difference between this end and that end of the air column. There should be a pressure difference at these two ends, then only the air column will get displaced. Otherwise, if the pressure difference is same, it cannot get displaced from one place to another. So here in this case, capital P is nothing but the small p, as you have remembered, P naught plus small p. P naught is the atmospheric pressure and small p is the increase of pressure, and capital P was the total pressure. So change in pressure, P minus P naught is nothing but small p. This is known as the excess pressure. Okay, so this will be small p, and dV is equal to the change in volume. We have let's say it is small p. Change in volume we have considered it small v. Therefore, dV is equal to small p. Okay, so far the work done is equal to P into small p into small p. This work done will be stored as a total energy of this air column. Okay, now what we are going to do, we are going to put the values of small p and small v from the calculation I have done earlier. Okay, if you remember your last class, then small p I have written as minus BA into delta. What is BA? BA was the bulk modulus of the air column. That means it is nothing but the elastic property of that column. Okay, and delta is nothing but small v by capital V is equal to how much? We have written as del eta by del x. So small v we can write capital V del eta by del x. This is expression 1 and this is expression 2. Okay, now we are going to put 1 and 2 in the equation of dV. Okay, therefore total work done, dW is equal to, we will write BA into delta V into delta eta by delta x. Okay, so the work done per unit volume, because in the kinetic energy case we have considered the kinetic energy density. So here we are basically going to consider the work total work done per unit volume. That means the total energy density. Okay, work done per unit volume, capital V, is equal to total energy density. We can write it as minus BA delta del eta by del x. Okay, and delta we have already defined as del eta by del x. Therefore, we can write BA del eta by del x whole square. Okay, here eta is the displacement of any arbitrary air column. Okay, and if we write eta is equal to eta m exponential I omega t minus kx, then eta dot del eta by del x is equal to how much? Eta m exponential this argument will be there minus I into k. Okay, so minus ik into eta. So we have to square it, then this value will be del eta by del x whole square will be equal to I square k square eta square. So I square is equal to minus 1, so this will be basically k square into eta square. Okay, so total energy density in this case, how much will it be its value? Total energy density will be equal to how much? We have to multiply BA with this quantity. So minus minus plus, energy, total energy is always a positive quantity, as you can see. So it will be BA k square into eta square. Okay, so this is the total energy density which we have obtained. Okay, now in order to find average total energy density, we have to take the time we have to take the time average of this quantity. And energy, since always is a real quantity, so what we are going to put, we are going to find out, we are going to put the real value of this eta. The real value of this eta will be real eta, how much? Eta m from this expression, as you can see, cos I omega t minus kx. Okay, so this is the real value of eta. So what it will be give us? Ba k square eta m square cos square omega t minus kx. Okay, this is the value of total energy density. Okay, so time, if we take the average total energy density, average total energy density, its value will be equal to, you have to take the time average 0 to t dt, then 0 to t, this whole thing, I mean BA into k square cos square omega t minus kx. Okay, and this is dt. Okay, eta m square. Okay, so so this value will 1 by t. So this value is this expression I have already calculated. I am not going to repeat it again. When you do the integration, you will find half into BA k square eta m square into t. Okay, so this t will get cancelled out, and finally what you will get, half into BA k square eta m square. Okay, now k is equal to, we know k is equal to omega by c. Omega is the frequency and the c is the velocity of the sound wave. So this will be equal to half BA omega square c square into eta m square. Okay, so half BA divided by c square omega square into eta m square. Okay, so BA divide over c square omega square into eta m square, this is the value of the total average energy density. Okay, now we have already know that c is equal to the velocity of the sound wave will be equal to, c is equal to root BA divided by rho naught. Okay, so c square will be equal to BA, sorry, c square will be equal to BA divided by rho naught. Okay, so we are going to basically put the value of c square here. So if we put this value here, what we will get, half into BA, in place of c square we will write BA rho naught omega square into eta m square. Okay, BA get cancelled out, so it is half into rho naught omega square into eta m square. This is the value of total average energy density. Okay, it's the value of energy density. Okay, now we know that total energy density is equal to sum of kinetic energy density plus potential energy density. Okay, so total energy density half rho naught omega square into eta m square. This value we have obtained. And if you see in the last class, what I have derived the value of the potential kinetic energy density, and the value of the kinetic energy density was 1/4 rho naught omega square into eta m square plus potential energy density. Okay, therefore the value of the potential energy density will be equal to this minus this, so it will basically give us 1/4 rho naught omega square eta m square. Okay, so one thing you have to remember that for such kind of sound wave, the potential energy density half into rho naught omega square into eta m square is equal to the kinetic energy density. So both the value of potential energy and kinetic energy density will be same. Okay, and because see, for kinetic energy density 1/4 rho naught omega square eta m square, the potential energy density is also 1/4 rho naught omega square into eta m square. So both these quantities are same. Also, as you can see, during the when the amplitude of the sound wave become maximum, and because eta m is nothing but the amplitude of the sound wave, then both the kinetic energy and the potential energy will become the maximum value. Okay, when eta m become maximum, the potential energy and the kinetic energy will also become maximum. So both the quantity becomes maximum when eta is equal to eta m. That is, at the moment the amplitude of the sound wave become maximum. Okay, so once we calculate the total energy, we can now proceed to the intensity of the sound wave, because total energy density we have already found that what is the value of half rho naught omega square into eta m square. So once we know the value of total energy density, we can easily proceed to the value of intensity of the sound wave. Okay, so in the next part we are going to do the intensity of the sound wave. So next part will be intensity of sound wave. Intensity of the sound. Okay.